Alright everyone, welcome to another Physics QBits video. This qubit is going to be focused on how to use this formula on the left-hand side to actually compute moments of inertia using this procedure I like to call chop, multiply, and add. And this is for those of you who are in kind of the AP level or undergraduate introductory level where you have to kind of use this formula to set up and compute these integrals for funny shaped objects. And so let's start by doing a little bit of review. So the moment of inertia of an object measures that object's resistance to being accelerated rotationally. This is kind of a lot, but what I want you to remember is that this is really analogous to kind of what mass tells us about translational acceleration. So let me write down a thing really quick. This is analogous to how mass tells us an object's resistance to being accelerated translationally. Okay, so what I mean is if we think about Newton's second law, right, we have F equals ma, right? And so the idea is for some given force, we can figure out how something is going to accelerate based on its mass. In other words, if I have a particular amount of force and I have a little tiny mass, right, that same amount of force is going to give me a lot more acceleration than before. On the other hand, if I have the same force, but I have a really big mass, right, then my acceleration is going to be really small because it takes the same force is going to have kind of less success in accelerating a much larger object, right? And so this is why we say things like mass tells us an object's resistance to being to having its motion changed. In the same way, right, if we write out Newton's second law for rotation, tau equals I alpha, right? If I have an object that has a very small amount of inertia, rotational inertia, or a small moment of inertia, right, I'm going to get a much larger acceleration for the same torque. And similarly, if I have the same torque and I have an object with a huge moment of inertia, right, I'm going to get very little acceleration for that torque. And so you can think of this as really just being the rotational analog of what mass tells you about an object when we're thinking about the kind of usual linear Newton's second law equation. Okay, so I wanted to point out a very weird thing about moment of inertia when compared to mass, right? So here's the weird thing. Okay, when we talk about an object's mass, every object just has a certain amount of mass, right? If I have like a box full of books, that box full of books is going to have some amount of atomic stuff in it that makes up its mass, that makes it hard to accelerate, right? So objects have one value of mass. We can just put it on a scale and measure how much stuff is in it, right? The weird thing is that objects have different amounts of moments of inertia. They can have multiple values depending on where you try to rotate them around or where you set the pivot point. Objects can have different moments of inertia depending on where the pivot point is. So, for example, let's imagine a rod like this. It has some mass m and some length L, right? Some mass m and some length L. And we fix it about the end. And then we take the same rod and we put a pivot point right in the middle. If we consult our physics textbook and we look at the formulas, it turns out the moment of inertia of a rod, not rot, about the end is 1/3 ml squared. And the moment of inertia of a rod about its center is 1/12 ml squared. And so we find out that if we try to rotate a rod about the end, it's actually 4 times harder to get accelerating than if we fix the rod kind of about its middle. And so what that means is rotationally, the rod on the left-hand side is a little heavier or more resistant to rotation, and the one on the right is a little bit lighter. And so this concept doesn't really exist for mass, right? If something has, a kilogram of mass, it's going to be the same to accelerate translationally. It just feels like it's a kilogram. And so this is why moments of inertia are a little bit weird. And one thing I want to point out at this point is whenever you're computing moments of inertia, make sure you're thinking about where this rotational kind of pivot point is, right? We can only talk about moments of inertia after we've specified where we're trying to rotate the thing about. Okay, cool. So that's all the review I wanted to do. Let's hop right into learning how to actually calculate moments of inertia from scratch. And so in order to do this, we really need two different facts. The first fact is how we actually compute the moment of inertia for a point particle. So imagine you have a fixed pivot point here, we'll label P. We have some rigid rod of length r and no mass. We'll assume this thing is very light. And we stick a point particle to the end of this thing that has mass m, right? It turns out that the moment of inertia for this point particle specified relative to the pivot point P is just m times r squared. It's the mass times the distance to the pivot point squared, okay? The other fact that we know is that when we have a composite system, to compute the moment of inertia of any composite system, you can just add the individual moments of inertia. So for example, let's imagine now we have a rod that has some mass capital M like this, and some length L, and we affix another point particle to the end, which I've drawn kind of big here, but let's call this lowercase m. We know that this thing, if we wanted to compute the total moment of inertia, is really the combination of a rod about its end, like this, of mass m, length L, plus the kind of point particle part of this contraption, of the same distance L away, but a lowercase m mass, right? And so it turns out that the total moment of inertia of this composite system, made of these two kind of different shapes, is really just the moment of inertia of a rod about its end, summed with the moment of inertia of a point particle from the pivot P here, right? And so this works out to be 1/3 capital M L squared for the rod's moment of inertia, plus the moment of inertia of the point particle, which is just lowercase m times L squared, the distance from the pivot point, okay? And so in general, if you have an object that is a composite thing of like multiple different shapes, you can really decompose it and find the total moment of inertia by just adding up all the individual pieces. So for example, like I1 plus I2 plus yada yada. And so what we're going to do is we're going to use these two facts to kind of come up with a scheme for computing moments of inertia of like weird potato-shaped objects. So let's move on to talking about how we actually decompose any object into point particles. So once again, I've kind of listed the two facts up here just to remind us. And then the idea we're going to use is trying to decompose any potato shape into just basically a bunch of point particles and add up the moments of inertia of those point particles to find the total potato moment of inertia, okay? So imagine we have some potato that looks like this, and we have our pivot point at some random location, right? The idea is we can decompose this object into little pieces of mass that are specific distances away. So for example, we can isolate a patch like this, and we'll call this dm1. And the reason I'm calling this dm1, right, instead of just m1, is because we're talking about an infinitesimally small piece of this potato. And so it's going to have an infinitesimally small mass. And what we're going to do is kind of integrate over the whole potato, okay? And so this little patch has a specific distance, r1, away from the pivot point. Then what we can do is consider the next patch over, okay? We'll call this dm2. And this dm2 has a different distance away from the pivot point, right? This is now r2. And so the idea is when we want to compute the total moment of inertia, we can take this dm1 times r squared, or in other words, this is going to be like I1, right? And we can tack on the moment of inertia, the contribution to the moment of inertia from dm2, which would be dm2 times r2 squared. And I've just realized I missed my subscript, right? And this guy is just the moment of inertia from the second little patch of mass. And we can continue this all the way kind of over the entire shape and compute the total moment of inertia by treating every single little patch as a point particle, right? And so this is where this idea of the moment of inertia formula comes from. This is I equals r squared times dm. And we're integrating over the entire shape. And I'll make this a little neater for you all, shape. Okay. And so one thing that I want to point out is this formula is like the most elegant way of explaining how we compute the total moment of inertia, but I really hate it because I think practically, right, it's pretty, but it's not super useful. When I look at this formula, I'm not exactly sure how to actually like plug stuff in and compute. And so what I wanted to do was kind of talk about the practical method for how to actually use this formula to do something with. Okay, so let's hop into a practice problem to kind of see how we might do this for an actual thing. And so I'm going to pick a one-dimensional shape. We're just going to use a rod about its end. And we remember the formula for this I've written down here on the right-hand side. Should be 1/3 ml squared. So we kind of have a target in mind. This rod has a total mass of capital M, and it has a total length of capital L. And we'll use these in order to compute the moment of inertia of this entire rod about a pivot point fixed at the end. And remember, right, here up at the top, I've drawn a little cartoon to remind us of our scheme, okay? What we're going to do is think about the rod as a collection of tiny little point particles, each of mass dm, and then we're going to add up all those point particles by using this integral, okay? And so the first step in our chop, multiply, add procedure is, of course, chopping the object up, right? So what we need to do is basically figure out how to parameterize or chop up the shape geometrically. In other words, what's the most useful coordinate to break up our shape into so that we can actually do an integral over a distance rather than whatever dm means, right? And so the advice I have for you here is to always pick a parameterization that gives you pieces of constant distance from the pivot point. For a one-dimensional shape, this isn't too bad. So for example, for this rod, right, what I want to do is slice up my rod into pieces that have a kind of constant distance. Because the rod is just a single line going left to right, then it seems to make sense to use the variable kind of x, the distance from the pivot point. Actually, let me change this from an x into a little dot so that we can see that this, I don't confuse you all with a bunch of x's, right? And what I'm going to do is think about this patch here as some random patch somewhere in the middle of some mass dm, okay? And so this way, I know that the parameterization that's going to be useful is turning this dm somehow into a dx integral. And I know that I want my boundaries eventually to run from 0 to L, right? I need to add up all the patches from the left end of the rod at x equals 0 to the right end of the rod at x equals L. Okay. And so now we've decided on a way to parameterize our object. I want to run my coordinate from left to right, and so I'll use x. And so the next thing we have to do is do the multiply part, right? So in our scheme, the idea is we compute the dm times r squared for every single little patch. And so I need to write my integrand in terms of this kind of dx integral rather than a dm integral, right? So I need to answer the question, what is dm in terms of my variable, in terms of x, okay? So what I'm going to do is draw this little dm kind of bit again, and we have our dx, we have our coordinate x, right? And so now we have the strange task of rewriting dm, the mass of this little patch, in terms of dx, okay? And so the thing I want to point out to you is that because this is an infinitesimally small piece of the rod, right, then it has some infinitesimally small length dx, okay? And so we know that we can write down a relationship between m and x here because we know that the total mass over the length gives me the kind of length density lambda, right? So what I can do is take the density and use that to compute the total mass of any small patch. Whatever mass, whatever size this little patch of mass is, right, with dx, if I multiply that by the length density, then I can compute the actual total mass of that thing. And so this equation tells us how to relate the mass of this little patch to the width of the little patch. Then we can just write the length density as a constant m over L. And so if I expand this guy here, this is m over L times dx. It won't always be the case that your objects that you're computing moments of inertia for are going to be uniformly distributed. In fact, some problems are going to have kind of like distance-dependent mass density. And so it'll be a little bit annoying, but we'll see kind of a more complicated version in office hours where we do a more complicated kind of two-dimensional varying mass version of this problem. And now we have a relationship between dm and dx. And so now we need to actually write our integrand out. So remember, our integrand is r squared dm, right? Where this guy here is the distance from the pivot point. And this guy here is the mass of the patch. And so in this case, right, the distance from the pivot point is whatever distance this patch is, or in other words, x. And so we have x squared on the left-hand side. And our dm is going to be determined by this relationship we drew up here in a box, or we wrote up here in a box. And so dm becomes then m over L dx, right? And so now we've totally written out the integrand, the kind of multiply part, in terms of just a geometric variable, this dx that we've chosen to integrate over. Okay. And so with this done, we can move on to the last part, which is the add portion of our procedure. And so for this part, what we need to do is actually substitute in the integrand into our integral. So remember, our integral is r squared, the integral of r squared dm over the whole shape, right? And then we can actually evaluate the integral if we've done everything correctly. So in this case, what I'm going to do is substitute the integrand we have from the last page up here, which is now x squared times m over L dx, right? We also know that the bounds of this integral are over the entire rod, right? So fortunately, we chose a very convenient parameter, the x-coordinate, and the x-coordinate for this rod ranges from 0 to L, the full length of the rod. And finally, we can look at this and recognize that this is a dx integral, and there's an x here, and this is a pretty nice integral to evaluate, right? So we can go right ahead and actually do this. And so the first thing I'll do is kind of take out this constant factor to make the integral look a little bit easier. And we have the integral of x squared dx. We know that the antiderivative of this guy is 1/3 times x cubed evaluated at the boundary 0 to L. And this is going to be m over L times 1/3 times just L cubed, right? If we do a little bit of simplification, then we can see that one of these factors of L goes away. And we have 1/3 times m times L squared in total. And so we have successfully, right, computed the correct value based on our textbook equation, okay? And so this is really all I wanted to show off. This is a pretty simple problem. And so if you want to see this worked out for kind of a more complicated shape that you might see on an exam or your homework or something, or a challenge, problem, go ahead and check out the office hours. But the main idea I want to emphasize to you is if you're frustrated with this equation, okay, I think you are perfectly reasonable in being annoyed about this equation. And so I think this is like a super useless formula, basically. And using this chop, multiply, add framework, you can kind of practically actually evaluate this integral by thinking about the shape as a bunch of different point particles, which is really what this formula is trying to tell you to do, but in very few words. Okay, so let's go right to the summary, and we can call it a video. And so the goal, right, of computing a moment of inertia is taking a shape and trying to figure out how hard it is to rotate. And the way that we're going to do this is by decomposing the object and computing the moments of inertia for all the little bits that make up that object, and then adding all those up, right? So that's what chop, multiply, add means. In this first step, what we should do is decide how to geometrically parameterize or chop up the shape. You should always be picking some parameterization that gives you pieces of constant distance from the pivot point. And so for a one-dimensional shape, what you want to do is pick little pieces that kind of have a specific constant distance from the pivot point, and then integrate over all the little patches from left to right. For something like a circle, right, the shapes that give you constant distance are concentric rings, okay? So what you want to do when you have like a circle shape or a disc-shaped object is take these little rings and see if you can compute the contributions to the moments of inertia from these little like tiny little washers, basically. And so while you're doing these problems, right, basically look out for what shapes give you constant distances, because we need this r squared dm, and we want this r squared part to be constant for every single little patch of dm that we're investigating. Okay. And once you figured out how to chop up your object, the next thing you want to do is write your integrand. So actually write out this r squared dm thing in terms of the distances you chose, and you want to convert this dm into some geometric measure, like dx or dA for areas or dV for volumes, right? So that you can actually evaluate this integral by using a geometric boundary. And the way that you do this is by answering the question, what is dm in terms of the geometric variable we chose. And finally, once you have this r squared dm chosen correctly, the last thing you need to do is just add up the actual contributions to the moment of inertia, or in other words, you can just fill in the integral bounds, plug in your integrand, and evaluate. If you find that something is missing here, what that means is likely your choice of parameterization variable is like the wrong one, or there's another detail you missed. One thing to pay attention to here is making sure that you have the correct kind of density relationship so that you can get the correct relationship between dm and whatever geometric parameter you chose, right? And so that's really all I have for you. I know this was kind of bare bones, and so if you want to see a more complicated version, please check out the office hours video where we'll do kind of a funny shape. And we'll see how to kind of work this out in the case that there's kind of some more wrenches that our teacher throws into the mix for us, okay? Other than that, thanks for stopping by. If you have any questions or comments, you can feel free to leave those in the comment section below, and I'll get to them as quickly as I can. Also, please don't forget to like and subscribe for more free physics problem solving tips. This has been Physics Tutoring Quantized.